Hey apes, I'm sorry this video is so late in coming. You can hear that my voice is still pretty shaky. I have been so sick and have not been able to have a period of time where I had enough voice without coughing in order to produce the video. So I'm going to do the best that I can in the hopes that you will be able to see this, take a look at it, and get some idea of what's going on here in these energy calculations. So just a couple of tips for the exam and how math works on the AP exam. So remember, this year you're given a calculator, which can help, but APES is really not about calculations. It's about math that you have to think through, and it's about real world math. Most of the math that we ask you to do are unit conversions or very straightforward math where we want to see that you understand the process of how the math works in environmental science. So it tends not to be particularly complicated in terms of what it is, but more of, do you understand how to set it up? Do you understand how to get from the units that you're given to the units that they want things in? I think the good thing about math in this way is it's math that you would actually use in your life. It's consumer math. It's math that will benefit you as you do cost-benefit analysis as an adult. Like, what appliance should I buy? Is this car a good deal? Those kinds of things are actually really important. So this math is real math. On the other hand, it's also the kind of math that you're not used to seeing in high school. We don't teach you those kinds of things, so it can be intimidating, since if this is the first time you've seen it, or if you're a math phobe. Remember that you will have a FRQ. It'll be your second one. That will be the first whole chunk of it will be math. Now on that one, you'll have at least 4 or 5 points that you can earn without doing the math, and we set it up that way so that people who are math phobic or who may not have had a APES teacher that has any strong background in math can still earn credit on that FRQ, and it doesn't sink them on the exam. It's just a way for us not to kill the exam scores for folks who may not be super strong in math. So I don't want you to fret it too much, but if you sit and you think for just a minute about this math, I promise you'll be able to set something up that probably will earn you a point somewhere along the line. A couple of things as we work through. You will need to know metric conversions in order to do any type of math they throw at you. They expect you to know the metric stair step. But if there's any type of conversion that is unique to the problem or unusual, they'll give it to you in the problem. They do not expect you to memorize those kinds of things. And also just a caution about boxing your answers or circling your answers. I know that in most math classes, you've been taught to box or circle your answers. But in APES, that's actually a bad thing. And here's why. If you circle or box your answer, then when I'm grading that, that's the answer I have to take. Sometimes there's mathematical calculations that you do wrong, and you actually get the correct answer, and then you mess yourself up and box the wrong one. If you box the answer, that's the only answer I can take. If you leave your answer unboxed and I can find the correct answer on your paper and I can follow your logic, then I can actually take that as your correct answer. So that does seem kind of counterintuitive, but in the APES world, it's best not to box your answers. And we as readers are taught to kind of be generous in figuring out, trying to figure out what your logic was and give as many points as we can. All right, so let's start with practice problem number 1. I've taken away all of the stuff at the top because you do not need that for right now. We do not need that when I'm just showing you how to work these things out. So the first one is asking how much energy in joules a 75-watt light bulb uses when it's turned on for 25 minutes. So let's talk about units here. Normally when we're talking about energy, we're talking about kilowatt hours, and of course we've got a our problem that's set up in watts and minutes. So we'll want to do some unit conversion in order to get that into something that makes sense to us. So the first thing that I'm going to do is I'm moving things around here. That's not what I meant to do. Give me just a sec. I'm going to make stuff. There we go. All right. I'm going to convert my 75 watts into kilowatts by dividing by 1,000. I'm using a really fat stylus, so I apologize for this. I wish it was a little bit finer, but this is what I've got. 0.075, that is a 0.075 kilowatts. Also, anytime there's a conversion, even if it's one that you can do in your head, you have to show your work, every single step of your work. And you have to make sure that your units are flowing throughout. There have been years, and it doesn't happen every year, it depends on who the question leader is, but there have been years where we cannot give points for a correct answer if the units are not carried throughout the problem. And that was actually the case last year, and it really made me angry because a lot of kids lost points on that. All right, so now we're at 0.075 kilowatts. And now we need to actually change our minutes into hours. So we have 25 minutes, and I'm just going to use an M because of my fat stylus. And I'm going to do a little dimensional analysis there, and we've got an hour on the top and 60 minutes on the bottom. And that's going to give me a little less than half an hour. It's 0.42 when we do the math out on the calculator. Okay, and that makes sense if you think about it. 25 minutes is slightly less than half an hour. I'm going to go up to the equations that were given at the top, and I'm going to rearrange that power equation where power equals energy divided by time, because here I want to solve for energy, and there it is right there. It tells me that. So here's my energy. I'm rearranging that equation up at the top, and I'm going to solve for E, and that gives me power times time. I promise that's a multiplication symbol with my fat stylus. So energy equals power times time. And when I plug in what I've already got here, my energy is 0.075 kilowatts. And I'm going to multiply that by my 0.42 hours. And I'm going to end up with 0.032 kilowatt hours. Now, I want to tell you kilowatt hours and kilojoules are actually equivalent units. So I'm going to do this out first with kilowatt hours, and then I'm going to convert it to kilojoules and joules. All of those kilowatt hours and kilojoules are actually the same thing. So that gives me 0.032 kilowatt hours. And kilowatt hours is a unit of power, but they want it in joules, and these things are equivalent. And I'm going to just put a big old slash here, which gives me, it's the same thing, 0.032 joules. Excuse me, 0.032 kilojoules. They want it in joules, so what I'm going to have to do is multiply by 1,000, because it's kilo, so it gives me 32 joules. And there's my answer. So, a 75 watt light bulb, when it's turned on for 25 minutes, uses 32 joules. All right, for number 2, we've got a problem that's kind of similar. It says a 100 watt light bulb is 20% efficient. The first question says, how many joules does it use in 12 hours operation? So that is actually the same problem as number 1, because we do not have to consider efficiency right now. The efficiency part is going to come in part B, where it's actually asking us how much does it convert to light. Because whatever its efficiency is, it's still drawing that same amount of power. So again, we're going to do the same exact thing that we did. We're going to take our wattage, and we're going to make it into kilowatts. So we've got 100 watts. I'll start all the way over here so I have enough room for my big fat pen. Got 100 watts. We're going to divide by 1,000 like we did before in order to get my kilowatts, and it's going to end up as 0.10 kilowatts, and that's a point there. Okay, and then I'm going to use that same equation that we did before, energy equals power times time. There we go. I'm going to plug in those numbers there. So we've got 0.10 kilowatts. I'm going to multiply that by my 12 hours. It's given in the problem. And I'm going to end up with 1.2 kilojoules, which is the same as 1200 joules. Okay. Now for part B, we have to consider the efficiency because that's what it's asking us. It's gonna we're gonna use what we got for A, and then we're gonna multiply that by the efficiency. So now we know how much energy it uses. From that, we got that from part A, but now we need to figure out how much it's actually converting to light. And it tells us that it's 20% efficient. So we're going to take our 1200 joules. We're going to multiply that by our 0.2, which is our efficiency. 20%, right? Times 0.2, and that's going to give us 240 joules. That's how much is actually converted to light. The remaining 80% is lost as heat. The third step in this, part C, says how many kilowatt hours does this bulb use, or does it use in 12 hours of operation? I'm going to use that same equation again. Energy equals power times time. There we go. And I'm going to take my kilowatt hours that I found from part A, which is my 0.10. I'm going to multiply that by the 12 hours again. And I'm going to get 1.2 kilowatt hours. Oh my gosh, that looks terrible. Now notice there that 1.2 kilowatt hours is the same as the kilojoules that we got up there, because again, kilowatt hours and kilojoules are equivalent units. So that the answer to A and the answer to C are actually the same answer. It's just two different units and they're equivalent, so it's just kind of pointing that fact out. All right, let's move on to number 3. An electric clothes dryer has a power rating of 4,000 watts. Assume a family does 5 loads of laundry each week for 4 weeks, and each dryer load takes an hour to complete. All right, so we need to find the energy that's used in joules and kilowatt hours. Okay, so we're looking for energy right there. And we need to go up and look at our equations that we've got there and figure out which one we want to use. Again, if we're looking for energy, we're going to use that same one that we've been using, that energy equals power times time, because that's our energy equation. All right, so we need to do a couple things to set this up, and the first is that same thing that we keep having to set up. We're going to get our watts into kilowatts first. So we've got all of our units consistent. So we're going to take our 4,000 watts, and we're going to divide by 1,000 to get our kilowatts, and that's 4 kilowatts. So one of the things that we have to do before we can solve for our E is, and that's our power, by the way, that 4 kilowatts, we've got to figure out what T is here. And they're giving us some information here. We've got 5 loads of laundry each week for 4 weeks. So when we're thinking about how much they're doing, you can kind of think in your mind that there's going to be some multiplication involved. Excuse me. So time, let's take our 5 loads. We're going to multiply that by the 4 weeks. So 5 loads a week times 4 weeks. And each one takes an hour to run. When we do that multiplication, 5 times 4 times 1 is 20 hours. Okay, so now we've got our time and we've got our power. Now let's solve for our energy here. So we've got, if energy is P times T, then we need to take our Okay, so we have what we need in order to proceed. So we're going to take that original equation, which is right here. We're going to plug stuff on in. So our energy equals our power, which is 4 kilowatts. And we're going to multiply that by our time, which is 20 hours. And we're going to end up with 80 kilowatt hours. Or 8,000 joules. Ta-da! Okay, so for part B, we need to find the operating cost of the dryer for 4 weeks of use, assuming that the cost of electricity is blah, 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 blah. Bleh. All right. We're going to take our answer from the first page, and we are going to, so that's going to be 80 kilowatt hours. And we're going to multiply that by the cost that they gave us, which is 0.0758. Per kilowatt hour. Kilowatt hours cancel out there. We're going to get $6 and 0.064 cents. So it's about $6.10 to operate that dryer for 4 weeks. Okay, so for number 4, you've got an air conditioner. It's a 7.25 kilowatt air conditioner. It's used for a total of 137 days, 24 hours a day. And the cost per kilowatt hours is 0.825 cents, and a kilowatt hour equals 3,400 BTUs. Okay, cool. We're not going to use all of that in the first part. We're going to end up using all of it on my part D. All right, calculate the total number of kilowatt hours used per year. All right, so we got to take our 7.25 kilowatts. This stylus is the pits. Y'all, I got to do better. That's a kilowatt. I'm going to multiply it by the 24 hours per day that air conditioner is running. And it is running 137 days out of the year. So that's going to give us 23,838 kilowatt hours. Groovy. All right, so determine the cost of air conditioning for a year. Well, we're going to use that number that we just came up with because that's how many kilowatt hours are used per year. And we are going to multiply that by the cost of electricity. All right, so 23,838 kilowatt hours. Remember to carry your units through because APES will want you to do that on the exam. And we're going to multiply that by your cost that's given in the problem, 0.0825. And we're going to end up with $1,967 to run that air conditioner for a year. Yikes. How many kilocalories are used per year? All right, so we got to go back to the front and we got to look at our calories per joule. Let me flip and see what that is. All right, 1 calorie is 4.18. Okay, got it. All right, so 1 calorie is equal to 4.164. Let me flip. 4.184. 4.184 joules. Cool. And again, remember, they don't expect you to memorize that kind of stuff. That will be given to you in your problem if you need it. So we're going to take our kilowatt hours, which remember is kilowatt hours and kilojoules are equivalent. So we can use that 23,838 and just call those kilojoules. So 20, good gravy, 23,838 kilojoules. I'm glad I'm narrating this because no one in their right mind could actually read this when I did this. We're going to multiply that by that factor conversion that we just did. 1 kilocalorie is, oh, by the way, so I've got a calorie over here is 4.184 joules. So a kilocalorie, if a calorie is 4.184 joules, then a kilocalorie is 4,184 kilojoules. Okay? And I converted and I'm multiplying in the same step there. So I'm using this conversion and I'm just making it from calories to kilocalories there. And remember, kilocalories and kilojoules are equivalent. All right, there we go. And we're going to do that, which ends up with this number, 23,838 divided by 4,184. And that comes up as 5.70 kilocalories. So this number, 23,838 divided by 4,184 equals 5.70 kilocalories. So now, excuse me, now we're going to use that BTU that they've got up there. So how many BTUs are used in a year? So again, we need our kilowatt hours. So 2,383, oh Lord in heaven, 23838. There we go. I'm looking back and forth at my papers here, and I'm losing my brain. Kilowatt hours. And we're gonna multiply that by our 3,400 BTUs. And that's per kilowatt hour. And we get 81,000,000,000 BTUs. Now, this is a number, 81 million BTUs, that would be really, really ripe to put into scientific notation. So if you wanted to do that, you can bump over 1, 2, 3, 4, 5, 6, 7. So you could always say 8.1 times 10 to the 7th BTUs, if that makes you happier. Either one of those would be acceptable on the exam. All right, guys. Oof, last one. Here we go. Thorpeville. Yay, Thorpeville. Thorpeville is a rural community with a population of 8,000 homes. It gets its electricity from a small municipal coal-burning power plant just outside of town. The power plant's capacity is rated at 20 megawatts, with the average home consuming about 10,000 kilowatt hours of electricity per year. Residents of Thorpeville pay 12 cents per kilowatt hour. Okay, groovy. The existing power plant runs 8,000 hours per year. How many kilowatts of electricity is the current plant capable of producing in a year? All right, it's a 20 megawatt plant. 20 megawatts. And we want kilowatts, so we need to multiply. There's 1,000 kilowatts in a megawatt. So that's going to give us 20,000. Yeah, 20,000. 20,000 kilowatts. And we're going to multiply that by how much it runs. 8,000. Wow, I really wish they would have made the number of homes and the number of hours it ran different, because now I'm all confused. 8,000 hours. Okay, 20,000 kilowatts times 8,000 hours that it runs, which is going to give us 160 million. Yeah. There we go. Kilowatt hours. Now, those are our 3 zeros at the end. Remember, I'm using a fat stylus. Again, this would be a great scientific notation one. So if we wanted to do that, we'd bump 1, 2, 3, 4, 5, 6, 7, 8. 1.6 times 10 to the 8th kilowatt hours. There we go. All right, how many kilowatt hours of electricity do the residents of Thorpeville consume in a year? Well, it says that each home consumes 10,000 kilowatt hours, and there are 8,000 homes. I think this one's the easiest one of the whole day. So we have 10,000 kilowatt hours. Cool. And we're per home. And we're going to multiply that by the number of homes, which is 8,000. Okay, y'all can all pitch in and get me a better stylus because this one sucks. And we're going to come up with 80 million. That's a lot. Kilowatt hours. And again, I would, if it were me, I'd put that into, I keep saying dimensional analysis, scientific notation. 1, 2, 3, 4, 5, 6, 7, 8.0 times 10 to the 7th kilowatt hours. That's a 7. Okay. So I noticed on this next one, compare answers A and B, and what conclusions can you make concerning the differences between the energy consumed and the energy needed? And there's an error there that should say energy capacity, not consumed, because the energy consumed is the energy that they need. They're consuming what they need. Part of what hopefully you picked up on in the chapters that you read, right, because everybody read, was that when a municipality or a town is building a power plant, you have to build for future needs. You can't just build for what your town or municipality needs right at that point. So when we're looking at these two numbers, we're seeing that the capacity of the plant right there is about twice what the residents use, and that's actually really good. That means that the municipality can grow, and the existing power plant is going to be perfectly adequate to meet the needs of the residents in the near future, even if the town grew, or even if their energy needs doubled. So the town uses about half of the plant's capacity. And this is actually a good thing for future planning because, like I said, the town can grow or the residents can use more energy and their existing power plant will be adequate for that. All right, D, if it takes 1 ton of coal to produce 2,460 kilowatt hours of electricity, how many tons of coal are burned by the power plant each year? All right, let's see. I'm thinking out loud. That we've got what our residents consume. So we got 80 million kilowatt hours times 1 ton per kilowatt hour. Okay, here we go. 80 kilowatt hours. And we're going to do some dimensional analysis. I don't know if y'all have noticed, but I switch between dimensional analysis and non-dimensional analysis. It's totally fine. It's whatever you are most comfortable with. It's the exact same thing. Some people are more comfortable with the railroad. And sometimes I'm more comfortable with the railroad, and sometimes, I don't know, my brain goes crazy and I just multiply it out like in my math class. I switch between chemistry and math style. All right, so we're going to divide our 80 million kilowatt hours by the kilowatt hours for that 1 ton of coal produces, which is 2,460. So we're going to get 32,520 tons of coal per year that are burned by that power plant. They should really switch to renewables. Okay, I hope that was helpful, guys. I'm going to go ahead and post this, and let me know if you have questions. See you guys tomorrow. Bye.